Find the absolute maximum and minimum values of f of x on the closed interval, -6 to 2. When you're asked to find absolute max and min on a closed interval, you are guaranteed to get an absolute maximum function value and an absolute minimum function value. We also know that it has to occur at one of the endpoints. So it's going to have to occur, either at, one of these endpoints or at a critical number that's in that interval. Okay, so the first thing I need to do is find my critical numbers. So again, I'm taking my first derivative. That's where I always get my critical numbers from. So I have 27x squared minus 108x plus 81. When I go to factor this, 27 is my GCF. I can factor that out. So take out the 27, and that leaves me with x squared minus 4x plus 3. And then this can factor a little bit further. So x minus 1, x minus 3. So my critical numbers are going to be x equals 1 and x equals 3. But if I look over here to my closed interval, -6 to 2, I only want values in there. So that means I am not going to include x equals 3 because it's out of my domain. So that means my absolute max and min have to occur at -6, 2, or at the critical number 1. So what I need to do is figure out which one has the greatest value and the least value. So I'm going to set up a table of function values. So I have to include my endpoints for my closed interval, and then again, critical numbers in there. All right, so go over to your calculator. I get -4,361. When x is 2, I got 31. And when x is a 1, I get 49. Again, these are function values, so I am plugging them into f of x. So my greatest y value is 49, so this is going to be my absolute maximum. And the smallest y value is -4,361, so this will be my absolute minimum will occur here. So like I said, one thing to keep in mind is relative local max and min are different, or are often different than absolute max and min. And we find them in different ways. Also, it makes a difference whether it's an open or closed interval. And we're going to do an open interval one next. Number 9, find the absolute minimum value of f of x on this open interval from 0 to infinity. Okay, so this time we're looking at an open interval, which means I may or may not get an absolute max or min. It's going to depend on what I find. Now with an open interval, if you have exactly one critical number in that open interval, then that will be an absolute max or an absolute min. If you have more than one critical number, like I said, maybe you do, maybe you don't. We have to kind of investigate the graph. So first step in either case is find my critical numbers. So I'm going to first start by rewriting f of x is equal to x plus 9x to the -1. And now I will take the first derivative. So I get 1 minus 9x to the -2 power. Now I have to see where this is equal to 0 or undefined so I can find my critical numbers. So setting this equal to 0, I have 1 minus 9 over x squared is equal to 0. There's a couple ways you can do this. You can, multiply through by x squared first to clear your fractions, or if you want to, move your 9 over x squared over and cross multiply. So there's options. So I'm going to go ahead and clear my fractions. So we're going to have x squared minus 9 is equal to 0. Again, here you can either factor or use the square root property. So I'm going to bring the 9 over. X squared equals 9, so x is equal to plus or minus the square root of 9, so x is plus or minus 3. So those are my critical numbers. So x equals a -3 and x equals a +3. But keep in mind, we want to be in this interval from 0 to infinity. So I'm not going to use x equals a -3. It's out of the domain. So that means I have only one critical number in my open interval. So that's going to be my answer. So right now I know that I'm going to have an absolute max or min, I don't know which one, at x equals 3. So I do have to figure out if it's a max or a min. You can either use the first derivative test or the second derivative test. So using the first derivative test, like I said, I've already got it found my first derivative. So I've got f prime of x is equal to 1 minus 9 over x squared. So doing a quick plus and minus chart, my interval's from 0 to infinity, so that's where I'm going to cut off my plus and minus chart. And again, I have the one critical number in there, 3. So if I use test point of 1, so I've got 1 minus 9 over 1. So 1 minus 9 is a negative. It's going to be decreasing. And then I'll use something greater than 3. I'm going to use 10. I'm using 10 because it's easy to compute. So I get 1 minus 9 over 10 squared. So 1 minus 0.09. So that's going to be positive, and it's increasing. So now you can see it's decreasing and then increasing. So that's going to be a minimum at x equals 3. Therefore, I have an absolute minimum at x equals 3. Okay. And let me just show you the second derivative test. Some students prefer to use this, especially in a case like this one here. But again, it's up to you which one you use. If I want to use the second derivative test to determine whether it's a max or a min, I still get my critical numbers from the first derivative. I just decide if it's a max or a min from the second derivative. So my second derivative, I'm taking the derivative, from right up here. So when I take the derivative, the 1 becomes a 0, so bring down my negative 2, so I have 18x to the negative 3. And now I'm going to evaluate my critical number. So I get 18 over 3 cubed, so 18 over 27. That's a positive number. It's greater than 0. So if it's greater than 0, that means it's going to be concave up. And if it is concave up, that means we have a minimum at the critical number. So like I said, it's just another way of classifying your critical numbers. So absolute minimum at x equals 3. Find the horizontal asymptote, if any, of the given function. Right, so if we have a rational function, we have, college algebra methods for finding asymptotes, or we can also use the calculus definition. So for an exponential function like this here, I have to use the calculus definitions. So recall that if the limit as x approaches infinity of our function is equal to some real number, and it has to be a real number, can't be positive or negative infinity, then y equals c is going to be a horizontal asymptote. And it's not just as x approaches infinity. Same thing happens if x approaches negative infinity. So if the limit as x approaches negative infinity of our function is some real number, then you have a horizontal asymptote. Oops, let me get the horizontal asymptote. Y equals c. Okay. So I have to look at the limits. So I take the limit as x approaches positive infinity of my function here. So 6 plus 5,000 e to the negative 0.07t. Probably the easiest way to find the limit, if you're using a graphing calculator, you can input the function there and then do a quick table. If you're not using a graphing calculator, you can still do a table. It's just going to take you a little bit longer to work it out. So I'm going to pick some numbers, like I said, on my table as x approaches infinity. This is an exponential function. It's going to get big really, really fast. So if you start with 10, 100, 1,000, a million, your calculator is going to be showing you errors right away. So if that happens, just start picking smaller numbers. So you might want to try like 1, 10, 20, and 50. I mean, you can try 100 and see what happens, but if it's, like I said, if it blows up, then start scaling it back. So you plug in some numbers in your calculator, and what you see is that this part here, as t gets really, really, really large, this becomes some really big negative number. So this is going to approach 0, this is going to approach 0, and what we're left with is y equals 6. If you look at the limit as x approaches negative infinity, and again, you can do a table, but as x approaches negative infinity, this is going to increase without bound. That's not a real number. The limit doesn't exist, so that doesn't give us a horizontal asymptote. However, when x approached positive infinity, I did get a real number. The limit was 6, so that's going to be my horizontal asymptote. So horizontal asymptote is going to be y equals 6. Find the vertical asymptotes of the graph of the given function. Okay. We have a rational function, so the easiest way to find the asymptotes is going to be using, college algebra techniques. You can still use the calculus definition. So, reminder from college algebra, if you want to find vertical asymptotes, we said, well, where do you divide by 0? That's potentially your vertical asymptotes. We have to check to make sure it's possible that it's a whole, but we always look at our domain. So I'm going to go ahead and if I look at this denominator here, so 5x plus 6, where is that equal to 0? And you can factor it or just set it equal to 0. I'm going to factor it. So you can see that when x equals a negative 6, I'm going to be dividing by 0. So that's probably going to be my vertical asymptote. There's one little thing though. So the vertical asymptote is if you plug it into the numerator, in the denominator you get 0 over 0. This is that indeterminate form. We looked at this way back in chapter 2 when we first studied limits. So if you have 0, 0 over 0, that's not a vertical asymptote. That's going to give you a hole in your graph. So really wherever the denominator is 0, but not 0 over 0. So if I plug negative 6 in the numerator, 3 times a negative 6 minus 9, negative 18 minus 9, that's not a 0. So that means I have a vertical asymptote at, I can't spell here. Vertical asymptote at x equals negative 6. So how would we do this without, using the college algebra way? How would we do it the calculus way? So like I said, in calculus, we're saying we're looking for some number c so that the limit as x approaches c is equal to positive or negative infinity. So you got to figure out what that c is first. You got to make a guess. And like I said, you're always going to look at the domain. If you have no domain issues, you're not going to have a vertical asymptote. But if like we figured out just a moment ago, we said, hey, we're not allowed to divide by 0. We can't have x equal a negative 6. So what I would do is I would look to see what is the limit as x approaches negative 6. Okay. And so again, you can use a table to figure out if it's increasing or decreasing without bound. And you would have to approach it from both the left and the right, and you may get different numbers. But what you'll find out is that it does increase and decrease without bound the closer you get to negative 6. So that's how you would verify using calculus that you have a vertical asymptote there. Find the horizontal asymptote of the given function. Okay, so here we have a rational function. And when we're finding horizontal asymptotes, we look at the degree of the numerator and denominator. And there's 3 possibilities. In this particular case, notice that the degree of my numerator is 3. The degree of my denominator is 3. If the degrees are the same, then you are going to get a horizontal asymptote. And it's going to be the ratio of leading coefficients. So it's going to be coefficients 2 over 9. So I'm going to, the horizontal asymptote is the line y equals 2 over 9. And that's it. That's all we have to do. If I want to find this limit using calculus, then, or find the asymptote using calculus, then I would take the limit as x approaches infinity or negative infinity for my function f of x. And then I would see what I get. So you can plug it in, you can use a table. One thing to remember is that as x approaches positive and negative infinity, the limit of 2x cubed minus 3x minus 9 is going to be the limit of that leading term. So I can just look at my leading term, 2x to the third. And the same thing for the denominator. I can just look at my leading term, so 2x to the third. Those will cancel and we get 2/9. So there's some shortcuts too you can use with limits. But worst case scenario, you do a table. Okay. Describe the end behavior of the function. For this particular example, f of x, we have a polynomial. And we know that polynomials are smooth and curvy. We also know that as you move out along the x-axis to the right or to the left, your graph has to either increase or decrease without bound. You know, it cannot go back and forth like this. It can't flat line. So with polynomials, we know it'll either increase or decrease without bound. So what we're really looking for is what happens? What's the limit as x approaches positive infinity? And then what's the limit? So that's as I move to the right. So to the right. And then I also want to look at the limit as x approaches negative infinity. So what happens as I move to the left? Okay. You know, if you're comfortable with doing limits, you can just do your limits. If you learned the arm dance when you're in college algebra, or you watched my other video on the arm dance, that's a nice quick way to work it out. So we're going to look at the arm dance. My leading term is 5x to the fourth. Now the degree is even. Okay, so even degree tells me that my arms are together. So that means both arms are up or both arms are down. The leading coefficient will tell you what your right arm is doing. I have a positive coefficient. Tells me my right arm is up. Right arm up. All right, so even degree, my arms are together. My right arm has to be up. That means I have both arms up. So I don't know what happens in the middle, but as I move to the right, I'm increasing without bound, and as I move to the left, I am also increasing without bound. So that means my limit as x approaches infinity is going to be positive infinity. I'm doing this here. And then as x approaches negative infinity, my y values are also increasing without bound. So it's going to approach, whoops, positive infinity. There we go. So that's my end behavior. And like I said, you can do a table. If you know the arm dance, do the arm dance.